Okay, so last time we did the estimation of proportions for the real population, okay, or estimation of real proportion of a population. In this we found the P actually, okay, and the confidence interval of P, it is equal to P cap, okay, which is the proportion, and it is equal to x by n actually, plus minus z alpha by 2 into p cap into 1 minus p cap divided by n. So this thing was for the single population or single we can say sample, okay. Single sample was taken from a single independent population, okay, and we estimated the real proportion for that population using the sample proportion. This is the sample proportion p bar, and it is equal to x divided by n, okay. X is the number that is happening and n is the total sample size. For example, we consider that out of 100 students of MBBS, okay, 70 gets good jobs, okay. Now 100 over here, this is equal to the sample size n, and 70 is equal to x, the specific things that we are interested in, okay. So the p bar over here is equal to 70 by 100 or 70%, 0.70 or 70%, okay. Now this is for the single population, okay. Now what if we find the difference between the proportions of two populations, two independent populations, okay. Now we will compare the proportions for two different populations that are independent of each other, okay. We say that if we are comparing the proportions of two different populations, okay, so if x1 is the binomial random variable with the parameter n1 and theta 1, okay. So if we have first population which has the parameters n1 and theta 1, okay, it can also be called like p1 bar, okay, anyone, either this or this. So if these two are the parameters of first population, and we have two independent populations, okay, and if n2 and theta 2 or p2 bar are parameters of the second population, we can say that the difference in their proportion, okay, this p2 or theta 2 is equal to x2 divided by n2, and theta 1 is equal to x1 divided by n1, okay. So this gives us the proportion for the two samples taken from two independent populations, okay. Just like we did it for the two sample means, okay. we do it for the two sample proportions, okay, and we will find the difference in the real proportions of the two populations, okay, using the sample proportions. Using the sample proportions, sample data, we find the real actual, the population difference of their proportions. So in this case, the theorem says that the confidence interval of this proportion difference will be equal to, let me write it down, so this is the confidence interval, okay, confidence interval of real populations proportion difference, okay. Now this is the proportions for the two populations, okay. P1 bar is equal to x1 divided by n1 and P2 bar is equal to x2 divided by n2, okay. Alpha is equal to 1 minus p, and p is the percentage confidence interval that we want to find. For example, we find 95%, for example, then p is equal to 0.95, so 1 minus 0.95 is equal to 0.05. This is the significance level of the population, okay. And this thing, actually, this is for the first population and this is for the second population. 1 minus pi bar, it can also be termed as qi, okay. So either write this one or write directly qi. I can also write the equation as, okay, I can also write it as p1 bar minus p2 bar plus minus, okay, z alpha by 2 into p1 q1 divided by n1 plus p2 q2 divided by n2, where q is equal to 1 minus p, q1 is equal to 1 minus p1 and q2 is equal to 1 minus p2, okay. So I can also write it like this one, okay. So now I will do an example on it and I will explain it while I am doing the example, okay. So this is the confidence interval when we have, actually the case is when we have proportions for two different populations, okay, or two different samples from two different independent populations. Okay, let's solve the example now. So the example, now I have taken it from the textbook that you sent me, okay. So the example says that if 132 of 200 male voters, okay, the sample 1, okay, is for male voters, okay, and it says that if 132 out of 200 male voters and 90 of 150 female voters favor a certain candidate, okay, running for governors of Illinois, find a 99% confidence interval for the difference between the actual proportions of males and females. Okay, now in the question we have taken two samples. The sample 1 is of 200 male waters, okay, and sample 2 is of 150 female waters. Okay, these two are the two different samples taken from two independent populations. Male has an independent population and female has an independent populations. Okay, they do not exclusively actually do anything. They are exclusive of each other, actually independent of each other. Both do not affect each other. So we have taken two samples from two different populations. So sample 1 N1 is 200 males and N2 sample 2 is 150 females. Now the X1 that is given, X1 is the population sample that is favoring certain candidate, okay, that is favoring certain candidate for governorship of Illinois. Okay, now so the X1 is here is in the first sample is 132 out of 200 females. It says that 132 voters actually favors certain candidate out of 200 total voters. Okay, and X2 is that 90 female voters. Okay, this is for male voters and this is for female voters. 90 female voters out of total of 150 favors the same candidate. Okay, and we want to find the 99% confidence interval of the difference in true population proportions. Okay, so the sample proportion for the male voters is equal to sample proportion, also known as P cap, is equal to X1 divided by N1. So X1 here is 132 voters out of 200. Okay, and the sample proportion or sample 2 proportion actually is equal to X2 divided by N2, and it is equal to total is 150 and we have 90 out of 150 voters. So these are the two proportions. Okay, now based on this data we want to find the proportions difference in the independent populations. So let me calculate these two. Okay, 132 out of 200, it will be equal to 0.66. Okay, 132 out of 200, this is 0.66. Okay, or 66%, and 90 out of 150, 90 out of 150, it gives us 60%, 0.60. Okay, now we have the two proportions and we know that the confidence interval is for the two differences actually. Confidence interval for theta 1 minus theta 2, it is equal to actually P1 minus P2. Okay, this is for the population proportion and this is for the sample proportion. Okay, this is the difference. Based on this sample proportion difference, we want to find the confidence interval for the true proportions of the populations. Okay, so it is equal to P1 minus P2 plus minus Z alpha by 2 into under the root P1 Q1 divided by N1 plus P2 Q2 divided by N2. Or we can also alternatively write it as P1 minus P2 plus minus Z alpha by 2 into P1 minus P divided by N1 plus this is P1, this is P2, 1 minus P2 divided by N2. Okay, 1 minus P1 is equal to Q1 and 1 minus P2 is equal to Q2. Now in this whole scenario we have P1 and we have P2. This is P2. Okay, we have P1 and P2 over here. Now these two are available. I need to find this thing and then this thing. So let's suppose 1 minus P1 is equal to Q1 and it is equal to 1 minus 0.66. So it will come 0.34, and 1 minus P2 is equal to Q2 is equal to 1 minus 0.60, which 0.4. Okay, now alpha over here, as we want to find the 99% confidence interval, so alpha is equal to 1 minus 0.99, which implies that we got 0.01, and alpha by 2, which will be equal to 0.005. okay, and z of 0.005, it is equal to, from the z table actually, or you can just write it in your calculator and you can find the value, and it is equal to 2.575. okay, this is the value. Okay, now we have P, Q, N1, this value and this value, so putting all the values. Okay, so the confidence interval, 99% confidence interval for theta 1 minus theta 2, the true proportion mean difference, is equal to P1 minus P2. P1 minus P2 will give us P1 is 0.66 minus 0.60 plus minus, okay, plus minus Z alpha by 2 is 2.575 multiplied by under the root of P1 is equal to 0.66 and Q1 or 1 minus P is equal to 0.34 divided by N1. The sample size first is equal to 200 plus. Okay, now the second sample has a P value of 0.60 and the Q value is 0.4, or 1 minus P2 is equal to 0.4 divided by 150 samples. Okay, so let's calculate it. 0.66 minus 0.60, it will give us 0.06 plus minus 2.575 multiplied by, okay, the numerator actually here, it will give us, let me calculate it, 0.66 multiplied by 0.34. okay, so 0.66 multiplied by 0.34, it gives us 0.2244. okay, so 0.2244 divided by 200 plus 0.60 multiplied by 0.4, it will give us 0.24. 0.24 divided by 150. So let's simplify it. We get 0.06 plus minus 2.575 multiplied by, let's get the value of this thing. Okay, so 0.24 divided by 150 gives us 0.0016. okay, 0.0016 plus, and 0.2244 divided by 200, it gives us 0.0011. Okay, now adding both these and taking the square root, we get 0.052. Okay, 0.06 plus minus 2.575 multiplied by 0.05217, so it will become 2. Okay, now further, the 99% CI is equal to 0.06 minus 2.575 into 0.0522 and 0.06 plus 2.575 into 0.0522. So calculating it, we get the final solution as 99% confidence interval of theta 1 minus theta 2 is equal to 0.06 minus 0.1343 and 0.06 plus 0.1343. So we get minus 0.074, and on the other side we get 0.1943. Okay, this is the 99% confidence interval for the true proportion difference of the two populations, two independent populations. Okay, so we see that it starts from negative and ends on positive, so it means that 0 p1 minus p2 is equal to 0 is somewhere in between. Okay, so when there is also 0 in between, it means that the difference is actually not significant, and we have a 0 value for p1 and p2 in between in this range. Okay, so when the difference is 0 in the real population proportions, it means that these two proportions are not actually significantly different. So the population's proportions, actually theta 1 and theta 2, are not significantly different from each other. It means that on both sides, for males and females, a kind of equal proportion of voters are turning out for the similar candidate, which means that we have like same proportion for males and females supporting the specific candidate for the governorship. Okay, or there is no difference, or there is no significant difference between the proportions. Okay, there is also a homework question, so if you want me to do it, I can do it also over here. but let me do that. That is the exercise problem. So I will also do the exercise problem on the same technique. Okay, so for the problems based on the true population proportion difference of two independent populations, we have another example, and it is from the exercise questions actually. Okay, and it says that among 500 marriage licenses applications chosen at random in a given year, there were 48 in which the woman was at least 1 year older than the man. Okay, so they took 500 samples. Okay, so the sample size for the first population is 500. Okay, and these were chosen at random, and there were 48 in which the women were 1 year at least older than the men. So x1 is equal to 48. So from this we can find the proportion of the first population is equal to 48 divided by 500. Okay, and further it says that, and among 400 marriage licenses applications chosen at random 6 years later, okay, there were 68 in which the woman was at least 1 year older than man. Okay, and then after 6 years of interval, okay, they say that they again made the survey, and the sample size and two chosen after 6 years was 400 licenses, and the proportion at which the women were found 1 year or at least older than the men was 68 out of 400. Okay, so P2 bar is equal to 68 out of 400. Okay, these two will give us the proportion of the samples, and based on these two proportions of the samples we can construct a confidence interval, okay, that represents the true proportion difference of the true population. Okay, so we need to calculate the p's, q's and z alpha by 2. Okay, and they say that construct 99% confidence interval. Okay, construct 99% confidence interval for these licenses. Okay, so for this what we need is, we need P1 bar or P1 cap minus P2 cap, which is the proportional difference of the two samples. We need this thing, and we need z alpha by 2. Okay, and as alpha is equal to 1 minus p, okay, well, p is the proportion of the confidence interval, so alpha is equal to 1 minus 0.99, and it gives us 0.01, and z alpha by 2 is equal to z of 0.01 by 2 is equal to z point 0.005, and it is very famous value, and we know it, I have memorized it, certain values, but you can also memorize it because it is very repetitive value, z of 0.005, z of 0.01 or z of 0.05. These are very repetitive in statistics, so once you start practicing you can actually know about it. Okay, so now we have this value, we have, okay, let me first calculate the proportions for the samples. For that, let me open the calculator. Okay, 48 divided by 500 of total licenses. So the first sample proportion that we got is 0.096, okay, or 9.6%. and the other one is 68 out of 400 licenses. It is 17% or 0.17. Okay, now we have the proportions of both samples. We have the Z alpha by 2 value, and the thing that we need over here is this thing. Okay, P1 into 1 minus P2 divided by N1 plus P2 into 1 minus P2 divided by N2 under the root. This is the pooled variance. Okay, we need the pooled variance over here for the two populations. Okay, now we know that the 99% confidence interval for theta 1 minus theta 2, it is equal to P1 minus P2 caps plus minus Z alpha by 2 multiplied by P1 into Q1 divided by N1 plus P2 into Q2 divided by N2. Okay, now what is Q1? Q1 is equal to 1 minus P1 cap, and P1 cap is 0.096, so 1 minus 0.096, it will give us the value of Q1, and Q2 is equal to 1 minus 0.17, so it will give us 0.83. Let me calculate the other one. It will give us 1 minus 0.096, 0.904. Okay, now we have two values, Q1 and Q2 also, so we have N1 and N2 also, so let's put it in the equation and find out the proportional difference of the two true populations. Okay, so the 99% confidence interval for theta 1 minus theta 2, it is equal to P1 minus P2, so P1 is equal to 0.096 minus 0.17 plus minus Z of alpha by 2 is equal to 2.575 multiplied by P1 into Q1. P1 is equal to 0.096 and Q1 is equal to 0.904 divided by N1 is equal to 500 plus, okay, the other thing is 0.17 multiplied by 0.83 divided by 400. Okay, so let's simplify this part and we can then find it out. Okay, so this will give us 0.096 minus 0.17, it will give us minus, this will give us minus 0.074 plus minus 2.575 multiplied by, let's calculate this thing also, so 0.096 when multiplied with the 0.904, it gives us 0.086. divided by 500 plus 0.17 multiplied by 0.83, so 0.17 when multiplied by 0.83, it gives us 0.1411 divided by 400. Okay, so let's simplify it further to get the value minus 0.074 plus minus 2.575 into under the root of, when these are added, it will give us under the root 0.00017 plus 0.000353. Okay, so these two when added, it will give us a value of 0.000525, 0.000525, and when taken the under the root square root, it will give us a value of plus minus 2.575 multiplied by 0.023 approximately. Okay, now multiplying these two and then adding and subtracting from this, so we will get 0.074 plus minus, now when these two are multiplied, and 0.023 multiplied by 2.575, it gives us 0.059 or 0.06 we can say. Okay, so first we will do the subtraction on the left hand side, comma, and then on the right hand side of the interval we will do the addition, 0.059. Okay, now doing the addition part first, when added to okay, so it will give us a value minus 0.015, and on the left side it will give us a value of, these two will add and the sign will be negative. So both two, when actually it will go into the addition but the sign will be negative because both have negative sign, so it will give us minus 0.133. okay, so this is the confidence interval. Okay, this is the 99% confidence interval for the true proportion difference, theta 1 minus theta 2, where theta 1 is the true proportion for the first population and theta 2 is the true proportion for the second population. Okay, so we know that when it starts from negative and ends on negative, it means that both the populations actually they have a significant difference. Okay, though it has the significant difference, okay, between their proportions. What it means is that after 6 years actually the age difference proportion was quite higher, and both the gap actually between 1 and 6th year they differ significantly. The proportion of women being at least 1 year older than their male counterparts during their marriage licenses is significant. The difference is significant. Okay, so just like for the population means that we did, okay, we said that the confidence interval for the population mean, which was mu, okay, is equal to x bar, which is the sample mean, plus minus into the margin of error, okay, and margin of error is actually, it was equal to the z of alpha by 2 or alpha, okay, into standard deviation divided by under to the root n. Okay, so just like we did it for the mean of the population, now we will do the estimation using the confidence interval for the variances. So instead of mean, here we will construct the confidence interval, okay, for the variances, the sigma square. Okay, this is the population variance, okay, for a single population. Okay, this is only one population, just like this one. This is the mean of a single sample taken from a single population, okay, and which represents the actual or real population mean. Okay, now to find or estimate the variance, actually we have a theorem. Okay, what this theorem actually says is that if S square is the value of the variance of random sample, okay, S square, it is a value of the variance of sample taken from a population, okay, and we know that sigma square is the variance of the population, okay, and we take it as this variance of sample, actually, it imitates or it represents the variance of the population, okay, and size of sample with size n, okay, this sample size is n, and the S square is the variance of that sample taken from a normal population. Okay, then the confidence interval or the interval for the sigma square, the population variance, actually it is equal to n minus 1 into S square, okay, divided by x square of alpha by 2 and n minus 1 degree of freedom, okay, and it is less than sigma square, okay, and sigma square is less than n minus 1 into S square divided by x square 1 minus alpha by 2 and n minus 1. So this is the confidence interval. This is the left hand side value, this is the right hand side value for the sigma square. Okay, so from the sample variance, actually from the sample variance, we actually calculate the population variance value, that where it will lie in an interval. Okay, we find an interval for the sigma square value, okay, and we say that we are this much sure, okay, that the population variance is in between these two values. Okay, so let's solve an example on this specific technique or this specific case, and then I will do an exercise problem also based on this. Okay, so the example actually says that, okay, the example says that in 16 test runs of the gasoline consumption of an experimental engine had a standard deviation of 2.2 gallons. Okay, it's okay. If we read the problem clearly, it says that in 16 test runs, okay, it means that the sample size is 16. Okay, so n is equal to 16 over here because the total test runs are 16. So in 16 test runs, the gasoline consumption of experimental engine had a standard deviation of 2.2 gallons. So it means that the standard deviation, okay, S for this sample, 16 sample, is 2.2 gallons. Okay, this is the standard deviation value S. Okay, and it is a normal population. It means that the population follows a normal distribution. Okay, so we have S over here and we have N over here. So if we see the formula, we have N over here, we have S, so we can find S square. Okay, we need to find this from a table, this also from a table. Okay, and then we can construct a 95%, or we can say, it says that compute 99% confidence interval. Okay, compute or construct the 99% confidence interval for the population variance, okay, sigma square. So how we can do it? We can do it from the sample variance. Okay, but we have sample standard deviation given. So from some sample standard deviation, if we square it, we find the sample variance. So we can say that sample variance is equal to S square is equal to 2.2 whole square. Okay, so it gives us a value of 4.84. Okay, this is the S square value. Okay, now we have N, we have S square. Okay, so now we have these two values. So let's put these values and find these X square, actually these values, from the statistical tables. Okay, I will show you how to find it also. Okay, so the chi-square value for alpha by 2 n minus 1 is equal to chi-square for alpha is equal to 1 minus p. So alpha is equal to 1 minus 0.99, so it will give us 0.01, and alpha by 2 will give us 0. Alpha by 2, 0.01 divided by 2 will give us 0.005. So chi-square of 0.005 and n minus 1 here is actually, we have n is equal to 16, so n minus 1 is 15. So chi-square for 0.005 15, it will be equal to, from the table, it will be equal to, okay, so this is the significance level that we want, 0.005. okay, you will be given this table in the paper. Okay, so, and the degree of freedom here for us is 15. So against 15 we come to this 0.005 and 15. So it will give us a value of 13.801, 32.801. This is the value of the chi-square. Okay, degree of freedom, df, this is 15, and we want it for 0.005, so 32.801. So we write it over here. 32.801 is the value of chi-square for 0.005 and 15 degree of freedom. Okay, now we also want the value of chi-square from 1 minus alpha by 2 and minus 1. Okay, so the chi-square value for 1 minus alpha by 2 and 15, so 1 minus alpha by 2 is equal to 1 minus 0.005, so it will give us chi-square of 0.995 and 15. So looking from the table, we get it as, okay, this is the P level that we want, okay, and we want it for 15, which is 4.601. Okay, so now that we have both these values, let's put it in the formula. Okay, so 99% confidence interval for sigma square, it is equal to n minus 1 into s square divided by chi-square value for alpha by 2 and n minus 1 comma n minus 1 into s square divided by chi-square value for 1 minus alpha by 2 and n minus 1. So putting the values over here, n minus 1 is 15 and s square is equal to 4.84 divided by the chi-square value for alpha by 2 n minus 1, alpha by 2 n minus 1, this is equal to 32.801. Okay, comma, and here it is 15 into 4.84 divided by the chi-square value here, which is 4.601. So making these calculations, we get 72.6 divided by 32.801 and 72.6 divided by 4.601. Okay, so we get the values as, the first value that we get is 2.213. okay, and the second value that we get is 72.6 divided by 62.6 divided by 4.601, which is 15.78, approximately 15.78. so this is the confidence interval for the sigma square or population variance. Okay, now I will do another example from the exercise. Okay, so the problem for the example from the exercise is actually problem number 53, and it is based on question number 30 actually. Okay, the data we will be using is from question number 30, but the exercise problem is 53. Okay, so the 30 problem, let me narrate it. It says that the length of the skull of 10 fossils skeleton of an extinct species of bird has a mean of 5.68 centimeter and a standard deviation of 0.29 cm. Okay, so the mean is equal to 5.68 cm. Okay, and the standard deviation s for the sample actually is 0.29 cm. Okay, now we have the sample standard deviation. As from this we can find the variance of it. Okay, and assuming that such measurements are normally distributed, okay, and it follows the normal distribution, which is a mandatory thing. Okay, it is normally distributed, so it means that the sample is from the n mu of standard deviation. Okay, and it says that find 95% confidence interval. Okay, so it says that construct 95% confidence interval for the population variance sigma square. Okay, so for that we know that the confidence interval for population variance, it is equal to n minus 1 to s square divided by chi square alpha by 2 n minus 1 comma n minus 1 s square divided by chi square 1 minus alpha by 2 and n minus 1. Okay, now we have n. Okay, n is actually in this example specifically, I guess it says 10 species. So let's see. Yes, it says 10 fossils. So n is equal to 10 over here. Okay, there are 10 fossil skeleton that were sampled. Okay, so n is equal to 10 and s square is equal to 0.29 square, which gives us 0.0841. Okay, this is the sample variance. Okay, now based on this sample variance and sample size, we want to find the confidence interval, 95% confidence interval for the population variance. So for 95% confidence interval, alpha is equal to 0.05. Okay, and alpha by 2 is actually 0.05 divided by 2. We get 0.025. Okay, alpha by 2 is equal to 0.025. So we need to find the chi-square value of 0.025 and n minus 1 is 9. Okay, n minus 1 is equal to 10 minus 1 is equal to 9. Okay, so it is from the chi-square table, and also we need to find the chi-square value of 1 minus 0.025 and 9, which makes us this is now equal to 0.975 and 9. Okay, we need to look up these two values into the from the table. Okay, we have s square, now we have n. So when we find these values from the table, we are good to go and put the values in the formulas. Okay, so let's use the online resources, okay, from the table and see what is these two values yielded in the table. So let's see. We need x square, the x square, or we can say that the chi-square, actually the chi-square value for 0.025 and 9. So we need it for 0.025. Okay, and the confidence interval is 9. So this is the value 19.023. We write the value over here, which is 19.023. 0, 2, 3 and okay. Now we need to find it for 0.975 and 9. So this is 0.975 and this is 9, which is 2.7. okay, so writing it over here. Okay, so this is equal to 2.7. okay, now we have the chi-square values also, so let's put it into the formula. Okay, so 95% confidence interval for the population variance is equal to n minus 1 is 9, okay, 10 minus 1, okay, and s square is equal to 0.0841, okay, divided by the chi-square value for 0.025 and 9, which is 19.023, separated by comma, and we have 9 multiplied by the numerator will be remaining the same actually, only denominator the chi-square value will change. Here we put 2.7. okay, so let's find out the solution. The numerator value that we get is 0.757. So let's divide it by 19.023. So on the left side we get 0.0397 and on the right side we get 0.757 divided by 2.7. okay, so we get 0.2803. 03 will, so we'll round it off to 2 decimal, we get actually 0.04 and 0.28, and this is the 95% confidence interval for the population variance. It means that the population variance according to this sample values collected, sample data collected, will lie somewhere between 0.04 and 0.28.